Welcome back. So we have discussed extensively about turbulent flame speed and about different experimental setups to measure those essentially. So now we will go back to essentially the turbulent flame modeling, and one of the most apart from the G equation model, one of the most prominent model has been the BML model, which is a Bray-Moss-Libby model proposed by Bray, Moss and Libby, and it's essentially a classic model in turbulent combustion. Okay, and it starts with this thing. It starts with the definition of a progress variable, which is essentially a non-dimensionalized reactive scalar variable. So the advantage is that if you define C, that is a progress variable, in this manner, that is C is equal to T minus Tu. Tu is the unbound temperature, and Tb minus Tu, whereas Tb is the bound gas temperature for the turbulent flame. And typically if it is a if there are not much heat loss, then this Tb will correspond to the adiabatic flame temperature, and T unbound is the unbound gas temperature. These are fixed values, this does not fluctuate. And so I will see that we can define C is equal to T minus Tu and Tb minus Tu in this manner, and then the advantage is that C always varies between 0 and 1. Okay, so and we can also define C in terms of a in terms of a mass fraction of a product, whereas Yp is divided by Ypb. Okay, so the PDF of we can assume the PDF of C as in this manner, that is we can say that the PDF of C is essentially given by this is a PDF of C at any point x and t. X is the position vector of that point, is given by alpha at that point xt, which is a parameter. And this is a delta function, which delta function is when C equal to 0 is equal to 1, and when C equal to any other value it is essentially equal to 0. Okay, so you can define this. D of x is equal to 1 and is equal to 0 when x equal to 0 and for x not equal to 0. Okay, so this is how a delta function is defined. So this essentially this delta function assumes the value 1 when C equal to 0, and plus this is given by beta times xt times delta function of 1 minus C. So when you have C equal to 1, then this delta function assumes the value 1 and otherwise equal to 0. So this is equal to 1 when C equal to 0, and this is equal to 1 when C equal to 1, and this is equal to 0 in all other cases. Okay. That is the point. Okay, and an alpha plus beta is equal to 1. That is how the probability distribution works, and this is essentially it's a PDF which is given something like this. So this is C equal to 0, this is C equal to 1, and this is alpha, and this is equal to beta. Okay, so this is how the PDF of essentially C looks like, and this is assuming a flame. This is essentially this type of model is only valid for a in the corrugated flamelets regime, where you say only C only varies between 0 and 1, and any other values is not possible. Okay, so of course C equal to 0 corresponds to the reactants and C equal to 1 corresponds to the products, and this way we can basically figure out where the location of the flame is. Okay. We can, using this definitions, you can also define a Favre averaged velocity at any point, and that is given by 1 minus C tilde. C here is the Favre average times u tilde plus C tilde times u tilde. Okay, this follows. Whereas the actual definition of alpha and beta are essentially the probabilities of alpha and beta are essentially the probabilities of finding the unburnt and the burnt mixture respectively. Okay, so this is what alpha and beta are. So now the one can derive an equation of C, just like what you can do is that you can since you have a temperature equation, you can put in the simplifications, that is your different terms. The radiation term is is equal to 0, and you invoke the distinct is the constant diffusivity and the Lewis number equal to 1 assumptions, and you can from the temperature equation you can just immediately derive the C equation, because C is just an algebraic function, it's just a some constant times temperature, right, some constant times divided by this is C is only just a algebraic function of a linear function of temperature. So, immediately you can from the temperature equation you can derive an equation of C. In this manner you can derive the equation of C, and then just like an equation of the reactive scalar, one can immediately derive a transport equation of C, which is C average C this is the Favre average C, and one can derive an transport equation of C tilde, which is given by this is the average density times dC tilde dt plus rho times U this will be U tilde actually this is U tilde times gradient of C minus this once again this scalar transport terms comes this U prime C prime, and then once again these are the fluctuating velocities, and then this is the divergence of this this term, and you have then you get this omega C tilde, which is the mean reaction rate. Okay, this is the Favre averaged mean reaction rate for this variable C. Of course, this is an equation for this you derive this averaged equation for C from that of a reactive scalar. So, of course, you will get a reaction rate term. So, this is the distinct difference between the mixture fraction model. In the mixture fraction model, even if you defined a variable which goes between z and 1, that was essentially a passive scalar variable, whereas this is a reactive scalar variable. And the reactive scalar variable equation has other problems. So, the first problem is essentially that you have to have this you have to have this this closure of these different terms, and you have to have the closure of the mean reaction rate. Okay, and then you have to have the closure of this scalar transport term. So, that is the problem. So, I'll show you the problem here. So, these are the two unclosed terms that we need to take care. Okay, so let's say we'll look into this term, we'll look into this term and these two terms separately. So, if we have these two terms, if we have a model, a good model for these two terms, then the whole problem of this transport equation of the mean C is solved. Okay, then the problem is that if you define this is your term to be closed U prime C prime, and that is equal to average of rho times, you can write it like this, and C minus C tilde this of course means this, right, this, and exactly it means this, just we have invoked the definition of U prime and C prime. Okay, okay, let's say it's not visible here, let's write it down the. So, this is the closure problem for this quantity. Okay. So, this can be exactly written as, in terms of the normal ensemble averaged, it can be written as this is just the definition of Favre averaging, right. Okay. And then we can model this as, we can write this implies is equal to this can be scaled as like this from here. Okay. So, this is this part, and then this part comes here, and this part can be written like this. Okay. by scaling arguments, right, on the overall. So, of course, this quantity is positive, this is C is always greater than 0 and C tilde is always greater than 0 and C tilde is always less than 1. So, this quantity is greater than 0, whereas U B average is of course greater than UU average, okay. Because of gas expansion, the bound gas velocities must be greater than the unbound gas velocity. This is of course for a one dimensional statistical planar flame that we are talking about here, okay. And then this implies that this is a positive quantity and this is a positive quantity. So, then it means U prime C prime, this is a positive quantity. Now, if we invoke the gradient transport assumption, we should have written, okay, we should have written minus U prime C prime averaged is equal to a turbulent diffusivity times dC dx, right. Now, then what happens is that because this quantity is greater than 0, this whole quantity is less than 0, this is greater than 0 and of course, this is also greater than 0 because it goes from 0 to 1 from unbound side to greater side. So, essentially you have a conflict. On the right hand side you have your entire term is essentially greater than 0 and on the left hand side you have a term which is less than 0. So, then it means then this is not, there is not gradient assumption, but there is counter gradient, there is not this assumption of this gradient transport is invalid for this type of turbulent flames in terms of the progress variable when you write in terms of the progress variable. So, progress variable does not allow you to invoke the gradient transport assumption because there is counter gradient diffusion that is taking place instead of the gradient diffusion, okay. So, this phenomena is called counter gradient diffusion, okay. And of course, this becomes less important when your UU prime is less than SL, okay, or sorry, when your UU prime is much greater than SL, that is when turbulent is very strong, okay. And then of course, when the reason is that this counter gradient diffusion is essentially considers both things, it considers turbulent mixing as well as gas expansion. So, the actually when you apply this gradient transport assumption, you consider only turbulent mixing, you use the gradient transport assumption to only model turbulent mixing, but here gas expansion because of this UB is greater than UU, this has complicated the picture, okay. So, that is what has made things more complicated. So, this is essentially a combination of this counter gradient diffusion contains both turbulent mixing plus gas expansion. So, this has to be kept in mind if you use to model this thing as if you want to model this progress variable average progress variable transport assumption and want to close this unclosed terms. So, then you have to be mindful of the fact that then in this C domain you have got strong counter gradient diffusion and that needs to be accounted. So, you have to find out situations when you have to use counter gradient diffusion or you have to use gradient diffusion. So, the other problem of course is the closure of this the same problem is of course the closure of this U prime C prime and it was closed in this manner. So, this 1 C tilde times 1 minus C tilde term stayed, and this essentially contains the gas expansion as well as the turbulent mixing in this form. So, this was closed by Venante, and this was the form that was taken. So, this was the form proposed by Venante, which was used to close this unclosed term, and this appeared to be a good model for this for to tackle this counter gradient diffusion problem. Now, of course, you still need to close for this term, that is the mean reaction rate, and that can be closed by this way. Whereas this model was proposed that this omega c ensemble average is equal to unbound gas density times the planar laminar flame speed times the stretch factor times some this constant g and coefficient and times the c times 1 minus c divided by L. So, there are several parameters that you see has come in. So, whereas this I0 is a stretch factor, G is a coefficient, and Ly is a crossing length scale which needs to be modeled. Or alternatively, I mean this thing actually feeds into this thing. You can model this whole thing as this entire thing as something called flame surface density, which is essentially the flame surface per unit volume. So, this much for the turbulent flames. So, what we have done, I mean if you just go through a recap of this whole turbulent flame thing, the most important thing is of course as you see here, once again I will show you this video, that you see this turbulence interacts with this flame at a multitude of length scales and it stretches and folds this thing. So, it is important to understand that and the most important property is that this turbulent flame propagates much faster than the laminar flame. But before going into that, what we need to address is that the different regimes in which the flames can behave in a very different manner. Okay, there are regimes in which the flame properties can dominate over the turbulent flow properties, but there are regimes in which the flow properties, the turbulence properties can dominate over the flame properties, and that can change the flame structure. So, we went into this thing called the regime diagrams, where we obtain different scaling laws, where we obtain different non-dimensional numbers, not exactly scaling laws, non-dimensional numbers in terms of this known turbulence and flame parameters, and we obtained this regime diagram, and which was plotted in U prime by SL and flame integral length scale by flame thickness. So, with these two are the most important regimes we identified for turbulent flame, most practical regimes. So, in this corrugated flame sheet regime, in this regime what was the thing was that the flame was essentially wrinkled by turbulence, okay, and but both the preheat zone structure as well as the reaction zone structure was essentially similar to that of the laminar flame, except the fact that it was bent, except the fact that it was stretched. Okay, but all these properties, internal properties could be considered same as that of the laminar flame, and this was the condition when your Karlovitz number was essentially less than 1. Karlovitz number less than 1 meant your flame thickness was smaller than the Kolmogorov length scale, which is a smallest scale of turbulence. Whereas in the reaction sheet regime, you had basically a structure where your essentially your preheat zone structure to be disturbed by the smallest turbulence eddies. This was because your Karlovitz number was greater than 1. Karlovitz number greater than 1 meant your flame thickness was essentially greater than the Kolmogorov length scale, which is the smallest scale of turbulence, and as a result of that your smallest scales of turbulence could penetrate into the preheat zone and distort the structure there. So, in this regime it is understood that along with molecular diffusivity your turbulent diffusivity might be important. Also, there is also another regime where well-stirred reactor regime, where your Karlovitz number, your reaction Karlovitz number was essentially greater than 1. So, it meant that your Kolmogorov length scales is essentially smaller than the reaction zone thickness. Of course, you remember the reaction zone thickness divided by the preheat zone thickness was equal to the Zeldovich 1 by Zeldovich number, which is a very small number as such, but still if your Kolmogorov length scale and the preheat zone, if your Kolmogorov length scale is smaller than the preheat zone than the reaction zone thickness, then it is expected that the Kolmogorov eddies can even distort the reaction zone and completely distort the flame structure, and the whole flame essentially behaves like a well-stirred reactor. But still there is no experimental verification of this regime, though there is experimental verification of these two regimes. But this regime boundary should not be taken with too much, these are not very rigorous as such, and these boundaries are kind of smudged, and but this gives you an idea about what kind of structures to expect. Okay. So, these are the different things that we had went through, and then we defined the flame speed. So, you see that this way by this process we essentially moved from our understanding of the laminar flame, planar laminar flame that we developed in the previous classes, and which allows us to directly smoothly graduate into turbulent flame. So, this is the turbulent consumption speed, which the flame displacement speed, which is essentially the rate of propagation of the surface. This is the rate of propagation of the surface propagation with respect to the local fluid velocity. So, the SD is essentially a relative velocity of the surface with respect to the local fluid velocity, okay, in the direction measured in the direction normal to it. So, this is the fluid velocity. And then we went to the concepts of flame stretched, and which is essentially the rate of change of surface area per unit original surface area, and we saw that the rate of flame stretch has two parts, the tangential stretch rate and the SD times the curvature. Essentially then we went into the different flamelet models, and which was like scalar variable G and progress variable C, and then we went into G equation where we showed that flame propagation can be described by the motion of an by the evolution of a variable where we consider the flame surface to be essentially an isosurface of that variable, okay, and then this isosurface locally propagates with this flame displacement speed, and then we can derive the G equation. And once again we need to put in some inputs into the G equation, and which came from our previous models where your SD can be the local input into the G equation, that is this needs to be inputted as a model, and that can be input by the which we show that it depends to the leading order on the flame speed, planar laminar flame speed, and then of course on the curvature and the tangential strain rate. Of course this was in the weak stretch limit, and then we went into a model for the turbulent flame, and then we showed that why the turbulent burning velocity is important. We showed that the turbulent by considering the mass flow rate into the wrinkle flame surface, we can define an averaged turbulent flame speed. So, by this way, and then we went on to find out the turbulent flame speed for the thin reaction zone regime, and we showed why turbulent flame speed is important. Then of course we showed you why we even recapped why turbulent flame speed should be proportional to the turbulent flame speed by local laminar flame speed should be proportional to the flame surface area by actual by the projected area or the planar laminar flame surface area. Then we showed different turbulent flame speed experiments, the state of the art experiments, and how the turbulent flame essentially propagates, and how the multi-scale structure of the turbulent flame emerges under the effect of turbulence. And then we showed you how why for an expanding flame the characteristic length scale should not be the only the length scale of turbulence, but the characteristic length scale of the flame should be the characteristic important, but the characteristic radius of the flame, the average radius of the flame should be the characteristic length scale when you want to define turbulent flame speed as a function of Reynolds number, because you have to remember that the turbulent flame speed is important. Turbulent flame speed is increased over laminar flame speed because you have the flame surface area is larger, turbulent flame surface area is larger than a laminar flame surface area. Now, the larger flame surface area is caused by stretching and wrinkling by turbulence at different lengths and time scales. So, only those scales of turbulence essentially which can disturb the flame structure, create new area should be considered, and for a kernel, for a spherical flame, only those turbulent structures which are of the order of radius or smaller than radius can affect the flame surface to create wrinkles, whereas turbulent structures which are much larger than the radius does not serve any purpose in terms of generating new area. So, that needs to be kept in mind, and that created this type of different scaling laws, and then we showed the new experiments in this turbulent flames, and then we showed the Bray-Moss-Libby model and the closure problem of the Bray-Moss-Libby model, where you cannot directly invoke the gradient transport assumption because C undergoes counter gradient diffusion due to gas expansion, and essentially this is an effect of both turbulent mixing and gas expansion. So, whether it will counter gradient or gradient diffusion depends on which wins turbulent mixing or gas expansion, and then we showed the models which can be used for essentially defining the mean chemical reaction rate, which is the other closure problem here. So, with that the discussion of the turbulent flame speed, the discussion of the turbulent premix flame comes to an end, and we will essentially this part of this course, that is where we discuss turbulent flames, which essentially originated from discussion of turbulent flows to discussion of turbulent combustion, then moving on to turbulent non-premix flames to turbulent premix flames. This part of the course comes to an end, and then we will move into the final part where we will discuss about practical combustors. So, see you then, and until then, goodbye.